Yeah, okay. Let's get started. Yeah, in our last lecture, we're trying to prove the channel coding theorem, right? So we'll start from the achievability or the direct part, okay? And so basically, we cover the idea of our scheme, right? So again, so we're not really designing a scheme, right? But we're just show, by this kind of construction, a good coding scheme can exist, right? That's our goal, okay? And then we use the idea of random coding, and then we want to compute the error probability, okay? And we start from computing the expected average error probability, okay? And that's basically what we did in our last lecture. So yeah, let's take a look at details because we need to continue the proof, right? So let's briefly go over what were we last time. Okay. Yeah, so basically this is the idea of random coding, okay? So basically what we do is that we generate this number of, we generate a number of code books, right? And how to generate the code book is like we have this number of code words for each code book, okay? And we generate them in an IID fashion, okay? So which basically means that the length of each code word is n, and each symbol is generated in an IID fashion, okay? So yeah, it's called random coding, okay? And then of course, the transmitter and receiver knows the code book, right? And then for the coding part, it's very easy. So we just label the first row as message 1, second row as message 2, and so on. Okay, so that's our encoding, the key part. I mean, this word really comes from the IID generation of the code word. Okay, and for the decoding, so we use the joint typicality decoding. So basically what we do here is that we find an m such that m hat such that x of m hat and y, they are jointly typical, and there exists only one m hat such that so x of m hat and y, they are jointly typical. Okay, if there's no such m hat and there is more than one, so we declare an error, okay? There's only one, right? Then we can say, okay, we can decode it, right? So that's the decoding, okay? That's the procedure, right? So any questions for the coding procedure? No, okay. So yeah, let me ask you, okay? So it's called random coding, right? So why we want to generate each symbol in an IID fashion, right? Of course, it's easy, it's simple, right? Yeah, but is there any other technical reason we want that to be IID? Right, just think about that, right? Don't look at your notes or right, see whether you can understand this, right? Use whatever you learned so far to try to see why we need that.
There's an upper bound. There's a equation for the upper bound that you that is log x, the length of the code, less equal to the power of negative hx.
Almost. Yeah, did you get what he said? Yeah, what he said is the cardinality bound or the probability of the typical sequence, right? Is that what you mean?
Yeah.
Right? So yeah, that's almost the answer, right? What I mean is that in order to use that, we need the typicality, right? And to use the typicality, the easiest way to use it is an IID sequence, right? So now we have to connect what we covered in our chapter 4 probably, right? When we introduce the typicality, we say, okay, for IID sequence, and then we define the typicality, right? And then we say, okay, how about for an ergodic stationary sequence? We can also use typicality and so on, right? So here, because we want to use typicality, then we just use the simplest case, which is IID. That is enough. Does that make sense? right? Yeah, so basically, my point is that, for this class, so I think the proof is fairly easy to follow, right? But we need to think, why we need this, right? We need to think a bit further, right? So there's a meaning for each step. Okay, normally in the book, people do not talk too much about, why we do that. It just show you, okay, if we do this, it works. But you need to ask why it is necessary or may not be necessary to do this. Okay? Very good. Yeah, so this is the encoding part. And then we start computing the expected average error probability, right? And the expected basically here means that we're going to do the ensemble average over all the realizations of codebook. Okay, expected here means average over all the codebook. Okay, and the average here basically means that average over all the messages. Okay. All right, and you can see, so the big advantage of doing this average or expectation over all the codebook is as follows, right? So after some manipulation, we can see that, so this average probability just equals to the probability that G, the decoding information of Yn is not 1 when the first one is sent. Okay, we only need to consider the first message, right? We do not need to consider all of them, right? So this is because we average over all the codebook, right? Because we consider all the realizations of the codebook, then it is totally symmetric. For each message, they are all going to be the same. Okay, so that's why we want this average over all the codebook, and that is one of the essence for the random coding. Okay, and now basically we need to compute the probability, right? So we denote the event when we make an error as E, right? And then we need to decompose the event to compute the probability of it, right? So the most common way to compute the probability of error in information theory and in coding theory and in communication theory, they are all union bounds. So we use union bounds a lot. Okay, you think union bounds may be very coarse, right? So I mean, we may overestimate, but eventually, normally the error is very, very small in practice. Okay, so even if we do union bound, it may not change the error probability a lot. Okay, because they are all very small. Right. So basically, here for this error event, we're going to decompose it into this number of sub-events, right? So the first event is that so this event is that so if the x n of 1, the first message, and the y, they are not typical. Okay, they are not in the typical set, then we have an error, right? And other events are, okay, there exists another code word that is typical with y, then we also have an error. Okay, that's how we decompose it. Okay, and as we said before, so we want to compute this probability, right? And then we use union bound, right? Union bound just to write them separately, right? And do a summation here. Okay, so next we just want to compute them one by one, right? We want to compute this guy, and we also want to compute this guy, right? There's a typo here, should be from 2, not 1, right? So 1 is here. Okay, I think this is where we finished in the last lecture. Okay, so now, yeah, let's have a new notebook. Okay, so today, okay, so hopefully we can finish the proof of channel capacity theorem. Okay, and then if we have time, or in the next lecture, we're going to talk about zero error codes. Okay, so let's continue. Yeah, so now our goal is to compute the union bound, right? So let's rewrite it. So it's a probability that G Yn not equals to 1 given m is 1, right? That is less than or equal to the probability of E1C given m equals to 1 plus the summation of I from 2 to to 2 power nr PREY given m equals to 1. Okay, so yeah, let's try to characterize it. Okay, so now let's see the first one. Okay, so the first one is that what is the probability that x1 and y, they're not jointly typical? Okay, what's the probability of it? Right, remember, so this x1, y, so those are the two random variables, right? So we use random coding to generate this, right? So this are jointly distributed according to what? P xn yn, right? Probably I will just normally this is how I write it as a vector. Okay, and if you want to really write it out, so basically we can decompose it because it's it's a DMC channel, right? So basically we can write that in this way: yi given xi, right? So this is a distribution. Okay, those are generated according to the real distribution here, right? And then from this fact, so what you can say about this probability? So this probability means that x1 and y, they are not jointly typical, right? What's the probability?
Isn't like the definition of like joint typical is like probability is 1, so like in this case it would be 0.
Exactly, right? So yeah, because with the probability almost 1 or less n goes infinity, so the probability they are jointly typical is 1, right? Therefore, so this guy would be less than or equal to epsilon for any epsilon, right? It's almost 0. Okay, so or it goes to 0 as n goes infinity. I'll write it this way. Goes to 0 as n goes infinity, right? Because they are jointly typical. Okay, so this one is easy, right? So it's almost 0. We don't need to worry about that. And then how about the second one here? Okay, how can we characterize that? Right, so this basically means that x2 or x3 or whatever other x is jointly typical with y, right? But they are not generated according to this probability distribution, right? So they are independent, right? For all other x who are not x1, so they are independent with y, right? Because that's for all other code word, right? Then does that remind you anything? So if they are independent with y, right, we generate x and y based on px times py, they're independent, right? And then what is the probability that they are jointly typical? Yeah, can you tell me that? What's the probability that they are jointly typical? Yeah, for this guy. Right, what is each individually, what does that roughly equals to?
Is it just like the 2 to the negative n?
Very good. And what?
H of x plus.
Almost. Mutual information, right? So remember, mutual information is to characterize this probability and also the cardinality bound of it. Okay? So then, based on that, we can say, okay, so this guy is less than or equal to, yeah, because now it's roughly equal, right? But we can have an upper bound of it, right? The upper bound, we need to make it a little bit bigger. So basically, what we can get is that, so there are in total 2 to the power of nr terms, minus 1 terms, right? And then, so this is less than or equal to this guy, minus 3 epsilon, right? So this is what we proved before, right? Remember, so when we talk about the joint typicality, so we have a few properties there, right? So we know the upper bound of the probability and lower bound of probability, right? And upper bound of the cardinality and lower bound of the cardinality and so on, right? So this is the upper bound. of the probability that, you know, if x and y are independent, what is the probability that they are jointly typical? Yeah. So does that ring any bell? Remember that? Okay, great. And then we can do some manipulation here, right? So for this guy, so we can ignore this one, obviously, right? So this less than this guy, and then multiply this, right? And then, so we can see this guy equals to what? 2 power of, we can combine this, right? So 2 n times I x y minus r minus 3 epsilon. Okay, so this is for the second term, right? And then, based on that, we can write the whole thing, right? So basically, for any epsilon bigger than 0, I say if for sufficiently large n, then, so this error probability expectation of the average error of the code book will be less than or equal to epsilon, right? So this epsilon coming from this epsilon, right? The first term, and add the second term, 2 minus n mutual information minus r minus 3 epsilon equal to that. And we can basically let this guy, for some n, so this guy will be less than epsilon, right? So then we can have this. Okay, so what does that tell you? So basically this equality tells you that, okay, so if the exponent is negative, and then as n goes to infinity, so this guy will go to 0, right? To make sure the exponent is negative, we only need to make sure this guy is bigger than 0, right? So basically the requirement is that if r is less than mutual information minus 3 epsilon, right? If r is less than this minus 3 epsilon, and then, so this guy will go to 0. Okay, so that's very good. Okay, so now we show that, okay, so if r is less than this guy, so r is basically the rate, right? So our goal is to show, you know, this is basically the capacity, right? So we're almost there, right? So this is what we want. If this guy is less than that, right? So mutual information is our capacity, right? And then the error will go to 0, okay? So that's almost exactly what we want, right? But now we need to solve 2 problems, right? The first problem is that, so we do not want the expectation here. The expectation is over all the code word, okay? So because what we want to go to 0 is the maximum error, okay? So here we have 2 things to take care of. Number 1 is an expected error over all the code book. Number 2 is an average error over all the messages, right? What we want is a maximum error, right? So there's a gap, okay? So we need to solve these 2 problems. Is that clear? Okay, the first problem is that can we get rid of this expectation over the code word? Can we? Or remember, right? So we don't need to construct the code book, right? So our goal is to show the existence, right? So now what we can tell is that, okay, if you have an error, right? If you average it over all the code book, it will go to 0. So it tells you that there must exist a code book such that the error of this code book will go to 0, right? Otherwise, there's no way it can go to 0. Does that make sense? That makes sense? Okay, great. So now let's write it down. Consequences. Okay, the first one is that, you know, for any fixed n, there exists at least one code or codebook that performs not worse than the ensemble average. Okay, means that there exists at least one code book such that the error of that code book will go to 0. Okay? That makes sense? Is that clear? Right? Okay, great. And in that case, so given that, so remember our capacity is not only the mutual information, right? So it's a mutual. We need to maximize the mutual information over the input distribution, right? Then we can manipulate the input distribution to maximize it, right? So then we can choose px to maximize the mutual information. Okay, very good. Okay, and then we can show that, so this guy will go to 0 eventually, right, as n goes infinity. Okay, and then we can say that, okay, so now R, as long as R is less than the maximum of mutual information over all the px, right, and then, so there exists a code such that the average of the error will go to 0, right? Is the argument clear? Okay, so now at this moment, so we show that the average of error will go to 0. We found a code. I mean, we didn't find that explicitly, but we know there exists a code such that the average error of error probability will go to 0, right? And then the condition is that R is less than the maximum of the mutual information over all the px. Okay, so this is where we are now, right? There's only one more step left, right? So we need to, go from the average error probability to the maximum error probability. Okay, so that's the last step. So we need to go from the average to the maximum error probability. Okay, how can we do that? Right, for this code, now we know the average of error over all the messages will go to 0, right? So how can we show the maximum can also go to 0? Or probably cannot, right? How can we manipulate? Maybe you want to design a new code based on this code, right? So based on this, existed code, so can we manipulate this code to show that, have a new code to show the maximum error will also go to 0? Would that be possible? Okay, so this is a very typical step, right? So from now on, after seeing this, so we do not need to argue this anymore, right? If you see, in all information theoretic paper, the only thing they show, is the average error goes to 0. Okay, they don't tell you, how to show the maximum error goes to 0 because it's a standard step. Okay, so this can be done as follows. It's called expurgation. Okay, so what's the meaning of it? Right, what's the meaning of expurgation?
Delete or erase it.
Very good. That true? Yeah. So basically it means we cut something off, erase something. Okay, let's see how we do that. So basically the idea is that, okay, so now we have a bunch of code word, right? So we know some of them may have a higher error probability, and some of those may have a lower error probability, right? So how about we remove half of it with a higher error probability, okay? And then we can show for the better half of the code, the maximum of error will go to 0 as well. So that's how we do that. Okay, let's see how we can do that exactly. So what we're going to do is that, okay, now let's say we found a code already, so in such that the average of error goes to 0, okay? So now we fix epsilon, okay? And we let our code, we call that Cn star. So this is the code we found such that the average error goes to 0, okay? So this be a code with the average of error of Cn star that is less than or equal to 2 epsilon, right? Why is 2 epsilon? It's because of this, right? So we say, okay, we find one, of this one code such that inside is less than this 2 times epsilon, okay, from here, okay, and the condition for that is R is less than C minus 2 epsilon, okay, and then what we do is that we're going to sort all the messages here, okay, and then find the worst half or the best half, okay. Then we sort the code word such that without loss of generality. So basically what we're going to do is that, so assume the first message has the best error, right? And then for the second, have this, and then the last one have the worst error probability. Okay? So yeah, let's assume this ranking, right? So you can do whatever you want, but you just need to fix the ranking here. Okay? For simplicity, we just say the first one has the lowest error and the last one has the highest error and so on. Okay? And based on that, so basically we just take out the first half of the messages. They're the good ones, right? So now we need to define a new codebook. Define the called expurgated code. We use Cn star tilde to represent that. So this is only the first half, x1, x2, x2 power n minus 1, right? So we get rid of the second half, the worst half. Okay, so basically this is the best half of the codebook. Okay, so why we want to do that? Right, because the average error is less than or equal to 2 epsilon, right? And we may have no idea what the maximum error is, right? But if we take the first half of the code, first half of the error probability, right? Then we will have an idea on what is the maximum error probability around the first half. Okay, it turns out that the maximum error probability of the first half cannot be too large. Okay, so let's try to prove it. Okay, so basically what we're going to do is as follows. So let's compute it, right? So basically, let's see how I want to write it. Yeah, maybe let me write the conclusion first, and then we'll prove it. Okay, so basically what we can show that the maximum error probability of this new code, okay, so that is equal to the probability of the last code word of this in the code book, right? Because we rank those from the smallest to the largest, right? So this guy will be the largest. Yeah, this guy will be the largest, right? So yeah, let's write it down. The probability of error 2 nr minus 1, right? So this is the largest error probability, and we can show that this guy will be less than or equal to 4 epsilon. Okay. Yeah, we denote this inequality as star, and now let's see how we can prove it. So basically, we're going to prove it by contradiction. Okay, so now let's see. So basically, yeah, now let's write down the Cn star first, right? So basically, the Cn star can be, let's write down all the error probability of the Cn star. So Pe1 Cn star less than or equal to Pe2 Cn star, and less than up to this guy. So this guy is where we stop, right? Cn star. Okay, and then this guy would be less than or equal to Pe2nr minus 1 plus 1 Cn star, and less than or equal to Pe2nr minus 1 plus 2 Cn star, and so on until the last one. Okay, so now what we can find is that, okay, so what if this inequality is now true, right? So basically it means that, so from here, so this guy will be bigger than 4 epsilon, right? Yeah, because we assume this is not true, okay? And this guy will be bigger than 4 epsilon, or bigger than, or yeah, right? And we can see that all of them will be bigger than 4 epsilon, right? Okay, and then we're going to show that, so this is not possible. Okay, so yeah, let's see how we can show that. Remember, so the average error probability for this code is less than 2 epsilon, right? So now let's see. So the only thing we can do here is that we just want to compute what is the average error probability of this code, and see, if all of them is bigger than 4 epsilon, this is still possible or not, right? Turns out that it's not possible. Okay, let's see how we can compute that. M equals to 1 to this guy, P-E-M. Okay, so it's a counting problem, right? We just compute that. So now what we do, so what we can see here is that, so this guy is bigger than or equal to this guy. Right? And then for let's see, for this guy, let's see how many items do we have there. Right? So basically, what we do here is that we just count these numbers, right? So we can ignore all of those in front, right? For those guys, so we just ignore those, and then just compute that. Okay, so then we can have a lower bound, right? Let's see how many number of items there we have. Okay, so this guy is all of those and plus this number. Okay, so we know this from here to the end is half of the code word, right? And then we need to consider this one more here. So basically, the total number of items here is 2nr minus 1 plus 1. And then we assume each of those is bigger than 4 epsilon, right? So this is how we do this. And then this equals to 2nr, right? And then, so we can multiply 2 inside. We have 2nr plus 2 times 2 epsilon, right? And then, so this equals to 1 plus 2 over 2nr times 2 epsilon. And clearly, this is bigger than 2 epsilon, right? And then we have a contradiction. Right, and then we're done with the proof. Right, so basically it means that if this guy is bigger than 4 epsilon, and then we have a problem here, right? The error probability cannot be less than 2 epsilon, right? And then we can conclude that so the maximum error here has to be less than 4 epsilon. Okay, so everything works here mathematically, right? But there's some tiny details we need to pay more attention. For example, right, when we compute the error probability, right, we need to find a lower bound. We need to ignore terms here, right? Why want to keep this term, right? Keeping this term is very important, right? We just need to keep one more term here, which is this guy, right? The reason we need that is we need this 1 here, right? Or we need this guy here to make sure this is bigger than 2 epsilon. Okay, so there's some like this subtle details, right? So we just need to be more careful here. Okay. Okay, very good. So now we're almost done. So basically we can see for this new code, right, which consider only the best half of the Cn star, right, for this guy. So yeah, we need to verify one thing, right? For this guy, we can show that the maximum error probability goes to 0, which is exactly what we want, right? So now we have shown, okay, we have a code book here, like this, right? We didn't construct that. We know there exists such a code book. Then in order to make sure the maximum error goes to 0, right? But we need to verify one more thing there, right? Because now the total number of code word here is halved, right? It means what? The rate is reduced, right? Before we showed, as long as, we are a little bit less than the capacity mutual information, we're fine, right? But now the rate is reduced, right? Can we still achieve the capacity, right? Because the number of code word there changed, therefore the rate is changed. Okay, so we need to verify one more thing, whether the capacity can still be achieved or not, right? We can see the logic. So now we need to verify. Okay, so our new rate, which is R star, let's see what that is, right? So basically that is as follows. So now instead of 2Rn, now we have this guy. If they are equal, if we don't have this -1, then we're fine, right? Because we show if R is less than mutual information, then we're okay. Okay, so but now we're not fine anymore because there's a -1 there. But now let's compute it, right? So it turns out that it's not so bad, right? So basically R tilde equals to what? We take this nr minus 1 out, we have nr minus 1, so that equals to r minus 1 over n, right? It basically means that R tilde and R are almost equal, right? When n goes to infinity, then we're still okay. We can still achieve the mutual information, right? Okay, and then we finish the proof, okay? Hence, so now we have constructed, actually we didn't construct it, right? But it's sort of constructed. We show the existence, a code, this guy, tilde, of rate R tilde equals to R minus 1 over n with maximum probability of error of this guy, max less than or equal to 4 epsilon. Okay, great. So that's basically the achievability part. We're done for the proof. Okay, is that clear? Any questions? Yeah, just think, now what you can do is that, you close your notebook and think, the procedure of the proof, right? How to construct the code book, right? And then after constructing the code book, and then we prove the expected error probability goes to 0, right? And then after showing the expected average error probability goes to 0, then we show, okay, there exists at least one code such that the error probability goes to 0, right? The average error probability goes to 0, right? And then we truncate the code, right? We propagated the code, right? And then have a new code to show, okay, the maximum error probability of this code goes to 0, right? And then we say, okay, so that will impact our rate a little bit, but this little bit impact 1 over n, it doesn't matter, as n goes to infinity, right? So that's basically the thinking process. Okay. And you may think, okay, why we want to random coding here, right? Why this randomness is so important? Okay, because that can simplify our computation. Okay, so this is achievability. It's very complicated, the procedure is, so that's one of the most significant contribution of Shannon, right? So we should be very careful on that. Okay, so second is the converse. Okay, let's see how we can show the converse. Right, the converse is the impossibility, right? We should want to show something that is impossible, right? So basically it means that we want to show there exists no codes with if the rate is bigger than the capacity C and arbitrarily small error probability. Okay, on the show there's no such code that R is bigger than C, then we can still achieve an arbitrarily small error probability, right? But directly showing that is not that easy, right? We want to show an equivalent statement, right? So basically that's why we call it converse normally, not called impossibility. So normally it is more convenient to prove that okay, suppose that a sequence of Rn codes Cn exists such that the maximum error probability so here we don't need to show the maximum error probability, we just need to show the average error probability goes to 0, as we said before, right? Such that this guy will go to 0, then it must be R is less than or equal to C. Okay, see whether it makes sense or not, right? So basically, if we show for any kind of code, if the error goes to 0, then R has to be less than C. Okay, so for information theoretic converse, so we always do that for channel coding. Okay, so let's see how we can do that. So basically, there's an assumption here. So we always use this assumption. So basically, what we do is that we let the message n follow a uniform distribution on n. later on we're going to discuss why it makes sense, right? But we'll always start from this. We'll assume what we transmit follows a uniform distribution. Otherwise, otherwise it still be fine, okay? But we're going to discuss that later. But normally for this kind of problem, we always assume that. Okay, that can make our life a little bit easier. Okay, so assume the message follow a uniform distribution. Okay, now let's see what we can do here, right? So now we're going to manipulate, right? So our goal is to show R is less than or equal to C when the error probability goes to 0, right? Okay, now let's see how we can do that. So this is for we need to manipulate some information theoretical inequality, right? So this step is relatively standard. Okay, let's see how we can do that, right? So first of all, because of this uniform distribution, and we can write NR as what? Right? NR is basically the rate of our message, right? From the source coding theorem. Okay, let's say if we have something that's uniformly distributed, what is the entropy of it? It's a log, it achieves the cardinality bound, right? Log of this guy will give you the entropy, right? So basically, this guy equals to the entropy of M, right? So that's why we need this assumption, right? Otherwise, this guy will be bigger than the entropy of M, right? But we need a less than or equal to, right? We need an upper bound, okay? That's why, we need to assume they are uniformly distributed. Does that make sense? Right? Okay, and then when we start our manipulation, right? Because we want mutual information, right? How can we came up with mutual information? Okay, so we learned that before. If we have an entropy, how can we create a mutual information? Right, that's a minus something, right? Then remember, mutual information of x and y equals to what? hx minus hx given y, right? So we just write this as hm minus hm given y. Then we just need to add this back. Okay. Okay, so now we have something nice. So this is the mutual information between m and y. Okay, and what is that? So does that remind you anything? So m is our source information, and y is our received information. We want to estimate m from y, right? So can we deal with that? What is that? Or can you give me an upper bound of the conditional entropy? So if you have nothing to do, right, remember what we learned before, the four inequality, right? The first one, Jensen, right? Second one, what's the second one? Log sum. The third one, the data processing inequality, right? And the last one, funnel. Now, in this kind of proof, probably you're going to use at least maybe 3 of those. Okay, so which one do you want to use? Which one is to bound the conditional entropy? So, funnel, right? Okay, so basically, by using the funnels inequality, okay, so this guy will be less than what? Anybody remember? So tell me the formula.
1 plus error probability log x.
Very good. What? Log? Yeah, log of the cardinality of x, right? So very good, which is NR. Actually, log of that -1, right? This -1 doesn't matter. Okay, very good. So, okay, so now we can have something nice, right? So basically, so this will less than or equal to the mutual information between this and that, plus 1 plus n p e n bar and nr. Okay, very good. And then remember, so from m to x, right? We have m to x and to yn, right? So it follows a Markov chain, right? If we have a Markov chain, right, because eventually we want the mutual information between x and y, right? Can we get something between x and y? We can, right? We use the data processing inequality, right? data processing inequality, and this guy will be less than this. Okay, very good. Are we done? Right? So now we have mixture information, right? So what is the problem now? Right, the problem of this guy. Right, what we want is the mutual information between x and y. Right, but now it's xn and yn. So we need to deal with that. Okay, how can we deal with that? Okay, so this is called single letterization. Okay, so if we divide n on both sides, we can show, we didn't assume anything here. We didn't assume it's a discrete memory channel, right? We didn't assume anything, right? So basically, if we divide n on both sides, and then we have 1 over n times this mutual information, n plus 1 over n, and plus the error probability, right? We let this guy goes to infinity, goes to 0, and then this and 1 will disappear, okay? It basically means that we can characterize any channel capacity as 1 over n times this mutual information. It's universal, but that is not useful, right? The reason it is not useful is that we have this n here, okay? If we want to compute it, it's very, very complicated to compute, okay? So we need to get rid of n, okay? So this is called single letterization, right? So that's normally, it's not extremely trivial to do, right? So we're going to do that next class, okay? But this is one of the major steps in order to prove it, okay? Thank you.